This video was sponsored by Dashlane. What you see here is an audio signal of my voice, which is something I'll say later on. And this here is a high-pitched pure tone that's much louder than my voice. We'll analyze these closely in a few minutes, but for now realize combining these two signals into one isn't hard mathematically. We just add the signals together, where you'll see the resulting audio is dominated by the pure tone, which when zoomed out like this just looks like a blue wall. The hard part mathematically though is taking this and getting my original audio back. No, you can't subtract because we'll assume we don't know how strong that tone originally was. But there is a way to extract the noise, or tone in this case, and get the original audio back. The math behind what just happened is where we're headed. This is also going to introduce a field of study that I think I'm safe to say most people have never heard of before, which also includes some math that most people will never learn, even though it's in a STEM-related major. But to begin, all we're going to do is simply plot a parabola in a way that's different from usual, and then from there it's going to get much more technical though, so stay with me. If we have the equation x plus 1 times x minus 2, it will of course be a parabola facing up with zeros at 2 and negative 1. But think about it like this instead. First, on our plot, I'm going to label the zeros with 2 circles. Then for any arbitrary x, this first term is really just the distance from x equals negative 1 that I'll label d1. So if x were 3, then this term would output 4. To see this graphically, we can put a dot at x equals 3 and see that the distance from negative 1 is 4. Then the second term in the equation is just the distance some arbitrary x value is from 2, and that gets multiplied by d1. So on the graph for some x, like we see here, we find the distance from negative 1, or 4, and the distance from 2, or 1. We then multiply the results, and this tells us our y value for that given point, which would be 4. See, that's all any y value really is, just the product of the distances from the zeros. When we slide that coordinate over and one of those distances becomes 0, then the product does as well, which is another way to see why this point has a y-coordinate of 0. Afterwards, d2 is considered negative, so we get negative y values, and from there we can just sweep out the entire function, taking the products at any x and mapping to the corresponding y, which of course makes a parabola. But now let's turn this into a rational function by dividing the same equation by x, for example, giving us this plot. In order to graph this like we just saw, we still, for any x-coordinate, have to find the distance from x equals 2 multiplied by the distance from x equals negative 1. But now this is all divided by the distance from x equals 0, and that will output our y-coordinate. So on our graph, 2 and negative 1 are the zeros again, and 0 would be the asymptote, but instead I'm going to call it a pole and label it with an x. For x equals 3, we have 2 of those same distances, 4 and 1, but the y value isn't 4 because we still have to divide by the distance from the origin, or 3. And this is why the y-coordinate is 4/3 at that point. Then since the closest thing to our point is a 0, as we slide towards it, that will, quote, win. That shrinking distance here makes the entire output go to 0 due to the multiplication. After that, we slide closer to the pole, and that will, quote, win. Remember, we're dividing by this distance, and when it shrinks to 0, we're dividing by a smaller and smaller number, sending the output to negative infinity in this case, aka an asymptote. Okay, so you guys good with that? Poles and zeros just refer to asymptotes and, well, zeros. Then the distance from those tells us the y-coordinates. Now, slight transition here, but we'll get back to that. In the real world, signals often come with a lot of noise, or like when dealing with stock market prices, the variations can make it look very noisy. So one technique to get a more general trend is to take a moving average, where you take some number of data points and find the average of consecutive ones, then just keep sweeping through the points, keeping track of the average as you go. With stocks, for example, this can smooth things out and remove brief drops or gains that aren't as meaningful when it comes to long-term changes. So let's actually do this for a cosine curve. To do so, I'm going to take samples of the signal at equal intervals. I can do this in many ways though. Like I could sample 4 points at a time, find the average for those y-coordinates and plot that value, then slide one over, take the average of these 4, and keep sweeping through the function. I could also do this for 5 points at a time, or 3, and so on. Then another thing I could change is the frequency that I sample at. But to keep it simple, we're going to sample every pi/3 radians. That's how spaced each interval will be. This makes the math easy because these would then be the y values of each point. We'll be averaging 2 samples at a time for simplicity as well. But here's what's important to remember. Averaging 2 samples can be written as the output of some arbitrary sample plus the previous all over 2. Like at n equals 2, this is saying take the second sample plus the first and divide by 2. And then when n equals 3, we average the second and third sample, and so on. I know it's kind of weird to say that x of n refers to the y values, but I do need to keep it like this because y of n is going to refer to the average itself that we'll calculate. This equation will show up again, so just keep it in mind. Okay, so finally to get to it, the average of the first 2 samples is 0.75, and I'm going to plot these averages on a graph below. Then the second and third sample of plus and minus 1/2 average to 0, of course. And I'll just plot a few more values where we get minus 0.75, minus 0.75, 0, and 0.75. This pattern would continue forever, so we get a periodic discrete function. From here we can connect the dots to get a sinusoidal function back, one with an amplitude of rad3/2. And it's got the same frequency as the function above. Now I want to emphasize this here. We can connect these dots with several functions, whether it be a sinusoid, a square wave, or something weirder. But the rule here is that the output must have, at most, the same number of sinusoids as the input. As in we only have one sinusoid here, which means we gotta have one here as well. For those that know what the Fourier series is, you know, for example, a square wave is made up of infinitely many sinusoids, so that can't be the output since infinity is, well, more than 1. And you'll note that this function is as simple as it gets. If I change the amplitude, then we won't cross all the points, and the same thing happens if I lower the frequency. Now, if I increase the frequency, we do eventually cross all the points again, but the output frequency must match the input, so we just stick with this. The most important thing to remember is that when doing a moving average sampled every pi/3 radians, the output samples lie on another sinusoid with an amplitude of rad3/2. These two numbers are the most important, so much so that I'm going to keep them on the screen. Now I'm going to lower the sample frequency of the top graph to every pi/2 radians. And if we average every 2 samples again, what you'll find is the outputs will go back and forth between 0.5 and minus 0.5. The simplest curve that connects these is also one sinusoid with an amplitude of rad2/2. This we'll also keep track of. Lastly, I'm going to lower the sample frequency again to every pi radians, and now the average of any 2 neighboring samples is 0. Even if we offset the samples, the averages remain 0. The sinusoid that connects these obviously has an amplitude also of 0. And the sampling of pi radians leading to that amplitude is the last thing I'll keep on the screen, because now things are going to start to come together and we're going to use the unit circle to see how. First, I want to put these angles where they belong on the circle. So like pi/3 goes here, pi/2 at the top, and then pi radians is on the left. So the angle is essentially our input, and those amplitudes are the corresponding outputs, which means pi would be the 0 since its output is 0, and thus I'll represent it with a circle just like before. Now remember from the parabola, the distances from the zeros were used to find the output. Well, on our circle here, the distance from the point at pi/3, let's say, to the 0 is the square root of 3, twice the output at that point. And the distance from the point at pi/2 to the 0 is the square root of 2, also twice the output at that point. This will in fact always be the case. For any point on the circle where the angle represents the sampling interval of our cosine curve, the distance from that point to the 0 divided by 2 yields the output of the reconstructed signal for a moving average done 2 samples at a time. Now I'll keep track of just these first 2 averages as we sweep the blue dot around the circle. This increases that angle and thus the sampling interval. But it also decreases the distance from the 0, which means the output amplitude will decrease more and more as we move around the unit circle until we eventually reach the 0. Now before we saw that the distance to a 0 can simply be written as x minus that 0. Well, here we're going to do the same thing, except we're not moving along the x-axis. So instead I'll call some arbitrary point z instead of x. And the distance to the 0 at -1 would just be z minus -1 or z plus 1. Pretty much just think of z as a vector, because now the vector z plus the vector 1, 0 gives us an output whose magnitude matches that distance, so this does work. But remember, it's half that distance which gives us our output amplitude that I'll just call y of z. Then also like before, let's see what happens when we add a pole at the origin, or simply put a z in the denominator. The new outputs will now just be the same things divided by the distance from the origin. But that distance is 1 and always will be as we sweep the circle. So adding a pole for our purposes doesn't change anything. The last thing I need to mention is that the input I was sampling this whole time always had an amplitude of 1. But had I changed it to like 2, then the output would have doubled as well. So really this equation gives us the ratio of the output amplitude to the input amplitude that I'll write as x of z. When that amplitude is 1, then we don't need to include it, but in general it does need to be there. So now check this out. I'm going to write that same expression up here and rearrange some terms. First I can divide both the top terms by z, giving us 1/2 times 1 plus z to the minus 1. And then I'm going to multiply both sides by x of z, giving us this. But I'll just distribute the x of z inside the parentheses. Now, anywhere I see x of z or y of z alone, I'm going to change it to x of n or y of n respectively. Then just go with me here, but by a certain mathematical transform I'll mention in a sec, anywhere there's a z to the minus 1 x of z, that will become x of n minus 1. The minus 1 is there because that's what the exponent was on the z, those must match. And the 1/2 can be written on the bottom like this. So hopefully you recognize this. It's what I said would show up later. This is the actual arithmetic of the moving average, summing two samples and dividing by 2. So the arithmetic we perform on the samples shown on the right, and the equation that told us the distance from the zeros and poles here on the left, along with the corresponding plot, are directly linked by something called the z transform. For those that know what the Laplace transform is, this is the discrete version. Now we can more quickly see what other kinds of sampling will do. Like if I want to do a moving average with 4 samples at a time, then the arithmetic would be this here, summing 4 neighboring samples and dividing by 4. Now doing the same thing backwards will change the x and y of n to x and y of z. When there's a minus 1, the z transform makes it z to the minus 1 x of z. Then -2 and -3 do the same thing with those corresponding exponents. Then since there's an x of z in every term, I can divide that out. And lastly, I'm just going to remove the negative exponents by multiplying by z cubed to top and bottom. This is the function that tells us everything we need to know. The zeros are -1, I, and -I, those are what make the numerator 0, and the poles are only at z equals 0, the origin. So I'll put those on our unit circle plot from before. The plus or minus I do go on the y-axis, as that's really the imaginary axis when dealing with pole 0 plots. Then for any sampling interval denoted by the angle, if I multiply all the distances from the zeros, then divide by the distances from any poles, and also divide by 4 because it was there in the denominator, that will tell me the output amplitude of the reconstructed signal for a 4-sample moving average. This 0 here at pi over 2 means as we slide towards that, the output amplitude also goes to 0, which we can see here since the average of any 4 neighboring samples now is 0. Now I've been using one sinusoid this entire time of one specific frequency, but that's really all we need in order to analyze any signal. Because look at what happens when we add 2 sinusoids together to get a more complex function and sample that at some arbitrary rate. If I do a 2-point moving average, the outputs oscillate between 0.5 and -0.5 as shown. The simplest sinusoid that goes through these is one with an amplitude of rad2 over 2 and a frequency that matches the first graph. The second function has been completely filtered out. And that's because sampling the third function is like sampling the two that make it up at the same rate, then adding the results. For the first one, the average of any two samples is 0.5 or negative 0.5, which is exactly the same as our graph on the bottom. So that yields the rad2 over 2 curve. And any two neighboring samples on the second plot output 0, which is why that was filtered out. Add those up and we get the final output. Now time for a huge correction I need to make. This entire video I've been using a really convenient sinusoid to make things work while I change the sampling interval. But had I used basically any other input frequency, everything would have fallen apart. However, one small change will fix that. Instead of this dot and the angle representing the sampling interval, consider those fixed, I'll just say at this rate, meaning they can't get any closer. So moving the dot around the unit circle now corresponds to changing the frequency of the input sinusoid as shown. Now once we get to pi over 2, we still see essentially the same thing. We have 4 samples per cycle and any two average to 0.5 or minus 0.5, yielding an amplitude of rad2 over 2. That hasn't changed. Instead, we just changed the input frequency to line up with the samples, and as a result the output frequency changes as well, but the output amplitude behaves the same as before. And as we keep going around the circle, we approach the 0, where again we see 2 samples per cycle, which always average to 0. This point will actually always correspond to your input doing 1 cycle for every 2 samples, whereas the top is 1 cycle per 4 samples, and these are known as normalized frequencies. Anyways, you'll notice that the higher frequency signals relative to the sampling get reduced a lot or completely removed, whereas lowering the input frequency causes the input to not get affected as much. That's why a 2-point moving average is also considered a low-pass filter. We can put in some function, but instead analyze the sinusoids that make it up and how those will be affected. You'll see the lower frequencies on the top get reduced a little or are allowed to pass, while higher frequencies on the bottom get reduced much more. Then we just sum those up and get the output of the moving average. In fact, I'll undo the filtering real quick, and you can see the higher frequency oscillations here get removed as we apply the filtering transformation. And no matter what a signal looks like, it can be broken up into sine and cosine functions, which we can analyze individually. The spectrum of those frequencies is known as the frequency spectrum, which is way more useful for complicated functions. And one example of a complicated function would be an audio signal of someone talking, like you can see here. If we zoom in, it looks sinusoidal-like, but it's also very chaotic. However, even this can be made up of sine and cosine functions of just different amplitudes and frequencies. See, if we have a single sinusoid, this consists of just one frequency. In terms of audio, it corresponds to a single tone. So if we made a plot of which frequencies are present, we just see a spike at 500 Hz in this case, the frequency of our signal. This would be the frequency spectrum. For two sinusoids, the function in time looks more complex, but the frequency spectrum would just be 2 spikes for the 2 frequencies. That audio signal would sound like, well, 2 tones. My audio signal, on the other hand, is made up of infinitely many frequencies, an entire spectrum, which the program I use, Audacity, has the option to plot. As you can see, most of the tones that make up my voice are in this region, between about 120 Hz and 1000 Hz. If my voice was deeper, those would be shifted to the left towards those lower frequencies or pitches. The peak spike here is around 460 Hz, but there are infinitely many tones in my voice, as you can see. Like even some random number such as 212.87 Hz. That tone is in here. It's a very tiny portion, technically infinitely small, but it's still there. So no, we don't speak in tones. However, anything that we say can be constructed by stacking infinitely many tones on top of one another and adding them up. But now what I'm going to do is combine my audio signal with a pure tone of a specific frequency that's much louder than my voice. As you can see, if I zoom in on the tone, it just looks like a sinusoid whose frequency in this case is 1000 Hz. So when I combine them, we get this, where that obnoxious tone is very apparent. One example of a complicated function would be an audio signal of someone talking, and okay, you get the idea. Something to notice though is that if I zoom in on the section in the beginning before I start talking, we just see the tone as expected. But if I scroll to the right a bit, we start to see these little variations. Those are caused by the signal of my voice, which was much lower in amplitude. But either way, my audio is still there making those changes. If I select the portion where I'm talking and we observe the frequency spectrum, we should see just about the same thing as before, but now there should be this higher peak right at 1000 Hz, indicating something of that frequency is dominating our signal as we know that it is. See, the frequency spectrum is much more useful than looking at the signal in time. And that's because the frequency spectrum allows us to do this kind of forensic analysis on the audio signal to see what really makes it up. But now what I want to do is remove that pure tone so we can get back the original audio. So we have this messy signal that is made up of my audio, which we want to keep, and a pure tone we want to get rid of. Does this remind you of anything we've seen already where a complex looking function made up of other frequencies ended up having one of those removed by some kind of filtering? Well, yes, the idea is if we sample a signal and do some manipulation with those samples, like a moving average, we can alter, or in this case remove, certain frequencies that make up the function, but not others. If the sampling has seemed kind of random this whole video, I've got some news. The signals I've been showing are really sampled signals, sampled at a constant rate. This is a discrete signal, and it's used because computers can't represent continuous signals that have infinite information. After analysis with these is complete, then continuous signals are reconstructed. But when it comes to applying this discrete signal manipulation, Audacity makes it easy as they include filters where I can just remove or amplify the frequencies that I want. What this will do is significantly reduce frequencies at and slightly around 1000 Hz, but do nothing to the rest. And when we apply a filter, we see the selected region has revealed the original signal, while the tone seems to be gone. On the other hand, I didn't highlight these sections, which is why the tone is still there. But now let's listen to our newly filtered signal. One example of a complicated function would be an audio signal of someone talking, like you can see here. Hey, that sucked. I mean, my audio signal was easier to hear, but it was really distorted and just wasn't good. So what's going on here? Well, for one, in the original audio signal, which we saw a spectrum of, there were tones at 1000 Hz and around it. So when we applied that filter which removed frequencies around 1000 Hz, that removed some of the original audio, which would cause distortion. Then the other thing to note is that digital filters are never perfect. They don't do exactly what you want them to do. I mean, there are other reasons why the program wouldn't do what we wanted, but in general, you can't make an ideal filter. In engineering, there's always trade-off where you get more of this one thing, but less of another. In fact, let's try to build the filter we just saw using the pole and zero plots from before, because this is where it gets more fun. If there's a specific frequency I want to remove, I just need to put a 0 at or near that point on the unit circle. And I'll put a pole along the same line but slightly closer to the origin. Also, these all come in conjugate pairs, by the way, so I got to include those down here as well. The reason for these locations is now for most frequencies, the distance from the zeros divided by the distance from the poles is roughly 1, which I'll plot. The output amplitude wouldn't really change. Now, since all the points along the unit circle correspond to a specific frequency, I'll let that be my x-axis. And as I sweep around tracking those distances, we get what the output amplitude would be. It's mostly 1, but at this frequency here and around it, it's closest to a 0, and that will, as I said before, win, sending the output close to 0. Then afterwards it goes back to about 1. This should look familiar, and it's known as a notch filter. Then from the locations of the zeros, real and imaginary, I can construct the numerator of the z transform equation, where the solutions to this, the zeros, would match what we saw. Then from the location of the poles, I can create the denominator, whose solutions would be those values. Hopefully this shows why those came in conjugate pairs, by the way. It's because we need real coefficients in this equation. From here we can apply the reverse transform and convert all the x of z's to x of n's and all that we saw earlier, which finally tells us the arithmetic to actually perform on the samples that will accomplish the filtering we want. So now let me just put this all together to give you the big picture. Real-world signals, which for the most part are continuous, often need to be altered in some way, whether it be filtered, amplified, reduced, or whatever, and this is often done digitally. Based on what we want to do, we can create a pole zero plot where distances at different points on the unit circle tell us how different frequency inputs will be affected. The locations of those zeros and poles, which are usually complex, will be the solutions to the numerator and denominator, respectively, of our transfer function, which is needed because with some z transform math, we can then get the difference equation that tells us what to actually do to the samples in order to accomplish what we want. Like you would program the computer to take a sample and multiply by 0.9, subtract 1.02 times the previous sample, and so on. Even previous outputs are used to create the next output. It seems random to do this, but after the original continuous signal is sampled and we sweep through those applying that seemingly random arithmetic, out comes new samples which when reconstructed yield a new signal that has been filtered as expected by the frequency response, in this case with one frequency or the pure tone being reduced nearly to zero. And this is where the design comes in, because now we can move the poles and zeros around and see exactly how the frequency response will change as a result. Having the poles closer to the unit circle than the zeros makes it so that only a narrow range of frequencies don't get reduced. Here's pretty much the moving average filter we saw before, which allowed lower frequencies to pass. And we can make much more advanced low-pass filters, bandpass filters, and so on. Little tweaks can have big effects on the response, but overall changing pole zero locations will change your z transform equation, and from there you just do everything we went over to get your new desired output. In analog systems, changing a filter may come down to turning a knob to increase resistance, or swapping out physical components. But all we have to do here to change the filter is maybe change a number in our code. That is the power of digital signal processing. An entire field you could get into, or a job title you could have. Beyond what I've said here, this applies to image processing, radar and sonar, speech recognition, music, financial data, cell phone transmissions, and much more. Basically anywhere digital signals are used, you can apply this. For all the young or soon-to-be electrical engineers out there, if you look at your course catalog, you'll see something like discrete time signals and systems, or digital signal processing, where the Z-transform, digital filter design, sampling, and more are covered. At my school, only the electrical engineers were required to take this. However, the computer engineers had to take the prereq, which is called continuous time signals and systems. And then some of them did take digital signal processing, but that was as an elective. At other schools, it wouldn't surprise me if other majors were required to take at least one class on discrete signals, but at my school, it was just the EEs. Overall, if the combination of math and programming like you saw here interests you, then this would definitely be something to look into. But lastly, I want to thank the sponsor of this video, Dashlane, a company dedicated to protecting your digital information. Dashlane is a password manager that actually does several things. One, it'll safely store all your passwords all in one place and sync them between devices so you never have to deal with resetting all those passwords you made months or years ago that you can't remember. With this, Dashlane will also autofill usernames and passwords for any site you have stored in their vault, making it just a little easier to navigate the internet. Something more important than remembering passwords though, is having secure passwords and being safe from hackers, which Dashlane takes care of. We're told we shouldn't store the same password for different sites, since being hacked in one place makes you vulnerable elsewhere. And with Dashlane that is solved, as you have the option to have them auto-generate very secure passwords to be stored and used across all your devices. You will have one single master password that you create when you sign up for Dashlane, and that is used to encrypt all others. So even if someone were to gain access to internal servers, they would just see gibberish. You, on the other hand, can feel safe knowing you have different and very secure passwords for each site, yet all you have to do is remember one single password. Plus, for added security, they'll notify you if any of your data has been compromised to give you complete peace of mind as you browse the internet. Pricing is already really cheap, but if you sign up at the link below or go to dashlane.com/majorprep, you'll get 10% off your premium subscription. Plus, there's a 30-day free trial, so no risk in just giving it a try. Again, links are below, and with that, I'm going to end that video there. If you guys enjoyed, be sure to like and subscribe. Don't forget to follow me on Twitter, hit the bell if you're not being notified, and I'll see you all in the next video.